point. I have to come up with a way to give you guys grades over the next 3 weeks, obviously. And since it's all review stuff, I am going to grade them. All these packets that I'm giving you, that I gave you on Friday, I'm going to grade. But there will be bonus attached to it. I'll have to figure out how. It can't obviously every problem is not going to be bonus. You're not copying any of this down. Do not copy any of this. It's not notes. I simply want to do about a 10-minute little review of stuff that when we got it back in the day, you guys originally did these review packets in Chem 1, and it was really fresh in your mind. You didn't have to really look at the top pages of this. You knew how to do these. But it's been, for some of you, 2 years, and for everyone else, 1 year since you've seen this. Actually, more than 1 year, really, because it was the beginning of Chem 1. We're at the end of Chem 2. So I wanted to kind of go over with you, and I won't do this for everything, but this packet here, probably the next packet, I'm going to give you like a little bit, like a 10, 15-minute little review, and then I'll give you like a couple of periods to get these done. Like, for example, the first 3 things we're going to kind of review about today are going to be the atomic structure, quantum theory, and the periodic table, starting with atomic structure. Do you remember how to do these? Remember this? Where you're given the number of protons, neutrons, and you're asked to figure out mass number, atomic number, the notations. By the way, the atomic number is the number of protons. It's another name for it. If you were to look, you should all be pretty much on this second page of the midterm review pack. I'm going to try to go in order here. So you've got some problems on the chapter, or the title of this is atomic structure. There's a lot of terms. There are a lot of terms under there. You are not going to need, in Chem 1, you didn't need to look over those. You pretty much knew how to do it because it was really fresh in your mind. I would like it if at the top of each of these packets, this time around, you actually look these things over. And if you find something you're not familiar with, like, for example, you don't remember what the 4 quantum numbers are, you better know what they are. You have to know what they mean, okay? And some other stuff on there, the Hund's rule, Pauli exclusion principle, filling up the orbitals and stuff like that. But this stuff right here, this is very, very typical, kind of an easy question. And if you get this kind of stuff wrong on the AP exam, you're really in trouble because there aren't going to be many that are this easy, but they will be there. So, for example, if I know I have 11 protons and 14 neutrons, what else do I know? I know the electrons are going to be 11 if it's a neutral atom, same number of protons and electrons. How will I figure out the mass number? I'm going to add protons plus neutrons equals the mass number. So I'm going to get, 25. And there's 2 kinds of notations you can see, and you may see on any test. The hyphen notation would just be the element's name, which you don't know what the element's name is. Yes, you do. Protons tell you that. 11 is sodium. So it would be just Na11. Or the nuclear notation would be Na25 over 11. Okay, like that. Mass number over the atomic number. Remember doing these?
Yeah.
Now, if I gave you different information, could you still do it? Here, I'm not adding anything. What am I going to have to do when I tell you I have 14 electrons and the mass number is 20? Yeah, because I got 14 electrons, I have 14 protons. To figure out how many neutrons, I have to subtract 20 minus 14, which will give me 6. All right? And his notation, again, I have to know who he is. 14 protons, that is silicon. And so what people do is this. Silicon 14, it's a very common mistake. Is that right? No, it's not silicon followed by his atomic number. It's silicon followed by the mass number, 20. Or SI 20 over 14. And of course, it looks like I didn't give you any information here, but you have every... What's that? Did I... What did I do wrong? Oh, great. I'm glad I'm taping this. Sorry. It's supposed to be 25. It's always followed by the mass number. I meant to point that out to you here after doing the first one right. But of course I didn't do that. But even I do that, we kind of like just look, we're so used to sodium. Oh, sodium's 11 sodium, and you write it right after it. But it's supposed to be the mass number. Because when I write it like that, so here it is where I'm giving it backwards. The mass number is right there. That's not looking up 17. 17, as you can see, is clearly not oxygen. It's chlorine. The mass number is 17. How do I know what oxygen's protons are? Well, you know what some people do? If it's like 18, they take half of it. A lot of times it is. A lot of times it's very close to being half. But it's not always going to be half. Oxygen, his atomic number is 8. And 8 is the number of protons. And you know that from the periodic table. It would also be 8 is the number of electrons, and the mass number is 17, which means he has how many neutrons in this case? Okay. All right. And by the way, last little thing before I leave this, the mass number is not the same exact thing as the atomic mass. They're often very, very close. We talked about why that is. All right? But the atomic mass is the mass of every element relative to carbon-12. Remember that? We compared everybody in the class. I did that as a little demo. Compare everybody in the class to one person I picked to weigh 150 pounds. And I picked somebody who was really small, 100 pounds, and then usually myself. And then basically we compared everybody, got a new scale. That's what they did for carbon. The mass number is always going to be a whole number. Those numbers are not whole numbers for two reasons. One, they're average atomic masses. They're averages of all the isotopes. Carbon exists as carbon-12, carbon-13, and carbon-14. All right? Hydrogen has 3 isotopes. That's why hydrogen's atomic mass is not just 1.00, whatever protium is. It also has to include deuterium and tritium. All right? And then you average them together. So there's a couple of reasons why those are not whole numbers. Their mass numbers will always be the whole numbers. All right? These guys are average atomic masses, and they're compared to carbon-12. They're relative to carbon-12. All right, good enough. By the way, the reason I chose carbon-12 is because if it's carbon-12, how many protons and how many neutrons does it have? 6 and 6, okay? And they made it, hey, they made his carbon-12's atomic mass and the mass number the same thing, 12. So that means the approximate mass of any given proton or neutron is going to be around 6. So you can pretty much tell the mass number is not going to be far off from the atomic mass. They're going to be pretty close together. All right, now let's get to the next thing, the atom. Let's talk about the atom. Now, we always draw, I talked about how the energy levels drawn like this are really a very poor representation. You don't really have circles, all right, going around in just one little, like the Earth goes around the sun. You don't have that, all right? You actually have electrons moving, speed of light. You never can tell where they are at any given time, okay? They're moving around in what I call electron cloud, all right? It's all about probabilities. And they generally tend to fill a particular shape, and that shape isn't always a sphere. That shape can be a sphere for the s orbital. Do you remember what it was for the p orbital? Yeah, it's like a dumbbell shape. Remember that? It was like 2 balloons almost. And then there's a d orbital and the f orbital. You don't have to memorize the shapes of all the orbitals. You should know the s orbital is a spherical shape. But even in that spherical shape, it's a cloud of probability where the electron is. It's not like, oh, there he is, and he's going around like the Earth's going to go around. I can predict exactly where the Earth's going to be, around and that's why we know what season it is. No, it's not like that. It's completely different. It's moving around, like I said, like a cloud. Now, and by the way, because of this, some other crazy stuff about this, they can absorb energy. They do some weird stuff. Electrons, they exist there, and then they get energy and they exist up here. What do we call that? When they just jump or leap. Yeah, they quantum leap. All right, they can get energy from a lot of different ways. We gave them energy in the flame test lab. Remember that? And in the spectrum tube lab, where we put electricity, they glow different colors. Why? Because they all have different electrons, all right, which are absorbing energy. They fall back down. They give off packets of energy, which we see as a color. Remember all that too. Okay. Now. You don't have to copy it. It's like I said, this is kind of a review. This is not on the packet. I need you to actually add something to it. Not the writing here, but 2 things. I never put on the midterm or the final, did I put this equation or that equation on there. Okay? They are on the AP exam. So what I'd like you to do is, there's no room on the first packet. On the second review packet, on the very back, I purposely left a blank page. At the very top, and don't write big because there'll be other things that'll be added probably over the course of the next few days. Write that equation right here, delta E equals hc over lambda. Write that on the top of the back page, which is completely blank. On the back page.
You said the second packet is the same thing.
Could you turn it over there, Olivia?
Yeah, turn it over.
And is it blank?
I'm just saying, it's the right packet.
Yeah, it's the right packet. Okay. And then this guy right here is the other equation you often know. And you don't even have to write down this stuff here, because if you look at these papers that you've already get to use, pretty much all of this stuff is on there. I highlighted some of them. I'm going to highlight more as we do them. These are the things that are on here. They give you Planck's constant. They give you the speed of light. All right, they will give you those kind of things. And they even tell you what lambda means wavelength, C means speed of light. It tells you all that, so you don't have to write that down. Just these equations are there too. But I want you to write them there because I want you to now copy these 3 problems at the top. Do not make them, leave a little bit of space for the work, but don't make them don't take up the entire back page with these 3 problems. Okay, this is what you're adding on to there mainly because I never did review this in Chem 1. I didn't put this onto your midterm or final. But of course it is, or is possibly on the AP exam. So copy those 3 examples down, and sometime over the course of the next, couple of, probably this week, you're going to be working on that one. Don't write huge, Emily. And then I'm going to do a little bit of a review of periodic table and quantum numbers a little bit real fast, and then you'll have the rest of this period pretty much all tomorrow to get that midterm review packet done. And for those of you who are watching at home because they're on the FBLA trip or whatever, there's a band thing going on. Same thing goes for you. Should make all these changes and start working on your midterm review packet.
What are we doing on Wednesday?
I don't know. I mean, possibly the next packet, possibly if that's a double period, I might have something to break it up a little bit.
No.
I have a lab I want to do eventually, so I'm going to do that one. Or if I'm just going to show you a video, because we don't want to, I mean, you can only review so many days in a row before you go crazy. So we will have some things to break it up. It could be Wednesday. See how it goes. Wednesday will be a double, right?
No, this is,
Oh, we'll be single, then we'll be working. We'll be doing whatever it is. I'm only going to do the extra stuff on a double period, where we have a little bit more time.
okay, because I won't be here, sadly.
Well, watch. If there's anything for you to know online, you just watch it. You'll see it.
No.
It'll be there. All right, so if you have all of them copied, hurry up. Copy fast. Because I don't want to waste the rest of this period. I just want to do a little bit more review for you. Some neat little review stuff that we haven't done in a long time, I'm sure. When I get to this next board, you're going to say, oh, wow, I forgot that's on there too. That was like from back in the 2nd chapter or 3rd chapter of Chem 1. All right. Like that. Remember the diagonal rule? Remember doing all these? Okay, doing the notations. I'm not exactly sure that they're going to do a whole heck of a lot of this on the test, but you certainly should be able to tell me, let's just do electron dot notations first. If I wanted to do electron dot notation, I don't even need to do this. How do I know nitrogen's electron dot notation? What would I just do? All it includes is the outer shell electrons, right? How many does nitrogen have? 5. Everybody see why it's 5? He's in group 5. So whatever everybody in group 5, everybody in group 5 is going to look like this. Wow, that's amazing. Everybody in group 5 is going to look like this. It's going to have 1, 2, 3, 4, 5. Right? So that's what nitrogen is going to look like. Now, if you wanted to do his notations, and again, I got to look this up because I'm not sure if they made changes or if they even are going to ask you about orbital notations for this. I have a feeling that they're not stressing that very much anymore. But just in case, if I had to do nitrogen, it would be 1s2, right? 2s2. Remember doing this? What will come after the 2s? 1s, 2s, 2p, right? And how do they fill up in the 2p? It's Hund's rule. How do they go in? One at a time before they come back and fill up, and it would look like that. Remember doing those?
Yeah.
Okay. And so you can always tell the order they're going to fill by the diagonal rule. I got lots of practice examples for you on the paper. I don't need to do a lot of that. Okay? However, there's something interesting about these guys. I can tell even more information by their periodic table, where they are in the periodic table. Take a look at this. Do you remember all this about the periodic table? This is the P block, the D block, the S block, and the F. That's kind of really important to be able to tell what orbitals are filling, what energy levels are filling, based on where the guy's located. I do not need to even know what element I'm talking about. If I just circle one of these guys, right? If I just circle, I can do it. Hold on. If I just circle this guy right here, I know his highest occupied energy level is going to be 1, 2, third row down. So he's 3. I know he's in the P block. So the last thing I'm writing for this guy is 3P, and he's the second one over 3P2, right? He happens to be silicon. You can see that from where he is over there, okay? He'd be ending at 3P2. Let's see if we can answer these kind of questions. Which of the guys up there, if you use this, or anybody in the periodic table, would have 5 valence electrons, and his highest energy level is 4. Energy levels are told by what row they're in, right? 1, 2, 3, 4. So he's one of these guys. He's one of those guys, right? And his highest, his 5 valence electrons tells me he's in group 1, 2, 3, 4, 5. So it's this guy right there. And who is that guy? I believe it's arsenic. Is that right? Yeah. All right. Last orbital to fill is 4p3. 1, 2, 3, fourth row down. P. 1, 2, third one over. Guess who it is again? Arsenic. Same thing. Looks like this, and he's in period 2. What does a period mean? A period is a row. These are all periods. This is period 4. This is period 5. Right? He's in period 2. He looks like that. So he's got 2 electrons in his outer shell. He must be that guy right there. And who is that? Beryllium. Right. And 6 electrons in the 3D sublevel. The 3D, remember, the D is always filling one behind. This is the 4th row, but that's where the 3D fills. And if you look back, if you were to look back at your, this, you'll see why. 3P, 4S, then the 3D, then the 4P, 5S, then the 4D. See, it always fills one behind it. Okay? So back to here. What was the question again? Has 6 electrons in the 3D. You simply count over and know where the 3D is filling. 1, 2, 3, 4, 5, 6 electrons. It would be what element? Iron. Now, by the way, there are exceptions to these rules, and that I did look up this year. They are not intersect. For example, chromium, copper, molybdenum, I think, and a couple of other guys do some weird stuff. Silver, because they're very close to having either a half-filled or a filled D sublevel. They actually can take electrons from their S, because they're very similar in energies. They're not going to, they said specifically, they're not going to ask those exceptions anymore. You no longer have to memorize those. So as far as you're concerned, what I'm giving you here is all you need to know. You don't have to worry about the exceptions. And then one set, notice how it can be worded difficultly. One set of paired electrons in the 2p. Now, some people will just see the 1 there, the word 1, and you'd be wrong. The 2p is obviously right here, and you say, oh, it's this guy right here. I said one set of paired electrons. Well, they're not going to pair up until each one has 1 electron in it. Then they come back and pair up. So this is going to be this guy right here. And who is that guy right there? Oxygen. In other words, if I were to write out oxygen, the 2p for oxygen would look like this. They go in one at a time according to Hund's rule, then they come back and pair it up. Now he's only got 1 paired. Okay? Those are the kind of questions on that 3rd page of your packet. They're asking questions like this. They're tough. A lot of people get them wrong. Okay. So, last thing about the periodic table. I'm almost done here. 2 things, actually, I'm going to show you. One is, you should really understand that all things change in the periodic table like this. And what I'd like you to do is draw on your 3rd page where it says periodic table there. I think it's the 3rd page in your midterm packet, which is what you're working on today anyway. It looks like this on this page right here. Okay? On the right-hand side, up here somewhere, draw yourself just a general shape of the periodic table. Just a general shape. We're going to label what the major thing is. So we're on the periodic table one. On the upper right-hand side there, in an empty space, draw just a general shape like this. And draw my arrow like that, too, because this is what happens. Everything in the periodic table changes from upper right to bottom left. Okay? You have your extremes at the upper right and the bottom left. For example, where do you think your biggest elements are? Bottom left. You're going to have your biggest atomic mass, the biggest radius, biggest atomic size. Largest radius would be down there. Up here is generally your smallest radius. Okay? Really? Well, now, let's try to use that one. If you remember when I taught this to you, I said, let's use that one to predict everything else we can. I predicted 4 other trends about him, or 3 other trends. Electronegativity, ionization energy, and whether it's a metal or a non-metal. Okay? Well, if these are the biggest atoms as they go down a group, right? I would expect, what do metals tend to do? They give up electrons, right? They lose electrons. So here, as I go down this group, I got larger and larger atoms. Here's a really small atom, hydrogen at the top. Then each time I go down, I'm adding an energy level, and the thing's getting larger and larger and larger. Those electrons out here, they're shielded from the pull of the nucleus for two reasons. The shielding effect, the inner electrons are blocking them, and he's so much further away from the pull of the nucleus anyway. Physically, the diameter's bigger. So, guys down here are your best metals. Guys up here are your best what? What do we call them? We don't call them metals. These are your best non-metals. Non-metals are guys that gain electrons. Metals are guys that lose. Okay, now here's a good question. Ionization energy. We're going to talk about ionization energy, even about the successive ones a little bit later, but not today. Ionization energy is the energy it takes to remove an electron. Where's it going to be easiest to remove an electron? Bottom left, right? You'd expect that. Okay? So it's going to have the lowest ionization energy. Lowest ionization energy for him, and the highest ionization energy for him. And by the way, there's another reason why. It's not just because of size. What else is happening as I go across a period? I'm getting closer to what? An octet. So it's much more likely that a guy over here is going to want to gain electrons to complete that octet than a guy over here who doesn't mind losing them because then he drops down to a lower octet, right? Which brings me to the last question, electronegativity, attraction for electrons. Who's going to have the strongest attraction for electrons? Upper right, right? Strongest, highest electronegativity. So write all these in here. I have them all written like in word form on that page, but I think one simple picture is worth 1,000 words. Here's your lowest ionization, or electronegativity, I should say. Okay? And remember, we can do multiple variations of this. Look at the different ways I can graph this stuff. Could you tell me what each of those graphs were? Let's take a look. What would that graph be? Well, the way to do this isn't to just, like, guess. Try to figure out what these are saying. If that's the atomic number, and this guy is 3, what element is he? Lithium. So this guy is lithium. And let's look right across the period. All the way across lithium. 3, 4, 5, all the way to 10. Here's 10. What's happening as you go across a period to this trend? Is it increasing or decreasing? It's decreasing. What do we know that goes down as you go across a period? Decreases. Atomic size, right, radius, exactly. And that's exactly what this is. This is atomic radius, or atomic size, whatever you want to say. Also, look what happens as you go down a group. All of these guys are in the same group. As I go down that group, they're getting bigger. All right, this is 3, 11, and 19 are all in group 1. And by the way, it doesn't have to be those 3. It could be these guys, right, I guess here, here, and here. They're also getting bigger as you go down a group. Now, the weird part about this is no one would be surprised to see that guy's decreasing across the period. This guy's increasing across the period. You would not be surprised if I told you that's electronegativity. Certainly a guy like fluorine over here is going to have a stronger attraction for electrons than the guy over there. No surprise. What's surprising is that trend. What trend is that? That's ionization energy. And it looks a lot like electronegativity, except for these crazy exceptions. Remember me explaining those exceptions? Yeah, it had to do with the fact, if we take a look at what happens there, see if you can figure it out. Hello? Yes. Yes. Okay. All right, so between 4 and 5, actually, and also between 12 and 13, what's happening is, well, I'll show you where that is on a different periodic table. Let's go back to this periodic table here. It's like basically between these two guys here and these two guys here. And maybe it makes a little bit more sense now that you see it. It should be harder to remove the electron from this guy over here than it is from this guy, but it's not. It's actually easier. Why? Because this one, for beryllium, this is beryllium over here, his last thing you wrote was 2s2, and it looks like this. But over here, you've got 2s2 and then 2p1. You see? It's just one electron in there. And it's in a P shape anyway. It's not as good a shape. It's not as stable. So it's a lot easier to remove, not a lot, but it's easier to remove that electron, even though it shouldn't be. Why shouldn't it be? It should not be hard to remove that electron. It should be a lot harder, actually, to remove that electron because he's closer to an octet, and he's actually smaller. Look at how much smaller it is. I've got the atomic size over here. You know, we're talking about from, where was it from?
4 to 5.
4 to 5. Here to here, much smaller. Matter of fact, even electronegativity, 4 to 5, is much greater. He's close to an octet. Where it doesn't do that is ionization energy because it's actually easier to remove that electron because he's in a P-shaped orbital and it's not filled, or even half filled for that matter. All right, that is it. I think that's the last one. Yeah. So your job, and for anybody who's watching, because there's a lot of people absent, and for you, Olivia, who's leaving, they just called from the office. You're leaving for an appointment, apparently. You guys should finish at least half of your packet today, the rest of this period, and more. And tomorrow, by the end of tomorrow, you're going to want to finish the entire midterm review packet. All right?
We're starting